Hello and welcome to my video about uniform circular motion. So there's a couple topics here, a couple definitions that we need to talk about first, and then we'll show the equations down there, talk about the formulas, and then we're going to talk about a couple example questions. So first of all, centripetal force is a center-seeking force. It's a description of a real force, or the better word to say it is it's the net force created by one or more real forces. Okay, so this is center-seeking. Centrifugal force is a fictitious force or an imaginary force, and it means center-fleeing. Okay, so it's an imaginary force because it's the force that if you have ever gone around on a playground on like one of those spinny ride things where it goes round and around and you feel like you're getting sucked outwards the whole time, that is the centrifugal force. It's the feeling of wanting to go the same direction that you've been going the whole time, which is going in the tangential velocity. But the difference is that you are going to be pushed inwards the whole time. Okay, so if you've ever been on one of these merry-go-rounds, you've probably experienced what I have, which is that you've got the feeling of getting sucked out to the sides. So you've probably had the feeling of going around this, and when you go around the merry-go-round, you get the feeling like you're getting thrown off to the side. But that's a fictitious force. There's nothing actually pushing you out. Okay? What there is maybe a friction or an applied force pulling you in. As you're holding onto those handles, you're applying a force. Or when your feet are on the bottom here, you're applying a friction force to pull you back in towards the center of that merry-go-round. So the centrifugal force is a center-fleeing force, but it's not actually real. It's just a feeling caused by inertia. The idea of wanting to keep going in the same direction you've been going the whole time. Okay, the tangential velocity is a velocity that's tangent to the circle. Oh my goodness, I'm using the word in the definition. Okay, here is what that actually means. Okay, at this moment, if you're going around counterclockwise, at this moment, the tangential velocity is exactly the velocity that is going tangent to the circle. Tangent is when you have this line here going up and down with the circle. So at this point, the tangent line is this way. At this point, my drawing is not perfectly great, but it's this way. At this point, again, my drawing is not perfectly great, but it's this way. Okay, so the tangent line is the line that is kind of going the same direction as the circle, but only for that instantaneous moment. Okay, so with all that in mind, we have a couple formulas here. We have AC, which is our centripetal acceleration formula. Okay, and we have two different formulas for that, but really we only have one formula for that because look at this one. This is our velocity, our tangential velocity, and if you plug it in for V here, then it's what causes this whole thing to turn into that. So really we only have two equations so far, and the second one here is caused by the second going into the first one. Okay, so two different equations, but I think you're given all three on your formula sheet. Okay, then we also are given, well, if we know AC is this, okay, and we know that a second ago I said F net equals the centripetal force, then F net equals MA equals the centripetal force, but A is centripetal acceleration. So instead of writing centripetal acceleration, we can just write this part, which is this whole thing. I'm going to use a different color. This whole thing going in to here. Okay, or you could do this whole thing going in to the same thing. Okay, so really, there's only two equations, the purple one and the red one, because the purple one creates the green one, and so there's really only two equations you have to know now. Other than, I guess this whole idea of net force being equal to centripetal force. Okay, those two things are equal, so you have to know that. Okay, yeah, that's basically the gist of it. So now let's see if we can do some actual calculations with this. Yeah, let's stop it right here so you guys can see this question a little bit better. Okay, the Whitemud to Terwilliger turn off in Edmonton is a sharp circle-like turn with a diameter of 100 meters. In order to avoid accidents, the turn is labeled with a recommended speed sign of only 40 kilometers per hour from the regular 80 kilometers per hour given on the rest of the Whitemud. Okay, the table of contents here, table of coefficients of friction are approximate and vary on the exact road conditions and tires, but I found all of these possible coefficients of friction depending on what is actually going on. So here is, I just took a Google Maps screenshot of that corner here, and you can see that it starts off straight and it kind of goes gently into the curve, and then this portion of the curve, about half, like the 180 degree turn part, is basically a perfect circle, right? Half of a circle, a semicircle. So that's what we're looking at, this red part in here. Okay, so given this speed limit, what is the minimum coefficient of friction required to avoid sliding out around this corner? Okay, so minimum coefficient of friction required to avoid sliding out. Well, what we're going to have to do is we're going to have to remember that we need to have a F net that is our FC. And our F net has to be MAC, but also our F net has to be force of friction. That's the only force that's going to bring you back in towards the center of the circle, is the friction of the tires on the road. So what we're going to do now is get a little bit more specific and go MAC equals, and then F of F is going to be mu times F of N, which again we can be a little bit more specific and call that mu of F of G in this example because there's no angles. So it would be mu mg. So MAC equals mu mg. Now we're looking for the coefficient of friction, so we're going to solve for that mu. So what we're going to do is divide by mg on both sides. What you're going to notice is that on both sides, the m of the car, the mass of the car, disappears and doesn't matter. So we're going to be left with mu equals AC over G. Now, AC is the acceleration towards the center, the centripetal acceleration. So we now will look at our possible options for the AC, which is the green or red options at the top. And since we're talking about velocity, we're going to pick the red one. So this is going to be v squared over rg. V squared over r is AC, right? So now we have this as our example, or as our formula. So now we can finally write in our numbers. The problem is we have kilometers per hour, so we're going to have to get kilometers per hour, and we're going to have to change that to 3,600 seconds per hour, and this is going to be 1,000 meters per kilometer. So it's going to be dividing by 3.6. Oh, and for some reason my calculator got very small. So this should be 40 divided by 3.6, and we get 11.1 meters per second. So anyways, this should be 11.1 meters per second squared over r, which is a 100-meter radius turn. And I based this off of Google Maps as well, so hopefully this is actually correct. And then our g, which is 9.81 meters per second squared. So when we put that all into our calculator, oh, that's the wrong button. There you go. When we put this all into our calculator, we're going to get that squared over 100 times 9.81, and we get 0.1258. Okay, so that is the minimum required coefficient of friction to avoid sliding out. Now, you can see maybe why they chose this speed limit, right? In Alberta, winter tires are not mandated, right? So all-season tires are basically what everybody has. Technically, you could have summer tires, which would be even worse, but those ones will then slide out. But all-season tires, assuming you have proper tread on them, will actually make it around the corner according to our data. And again, it varies on exact conditions, right? So you always have to drive to the conditions of the road. But all you need to have is 0.13 for your coefficient of friction, and you can make it around the corner. And so mostly you should make it around the corner. Now, winter tires are even more likely to make it, right? So you can kind of see all the different possibilities, but in the summertime, we should have a wildly different answer. So let's keep going. Let's take a look down here and look at part B. Given that it is winter many months of the year, is the speed limit low enough during those months? If not, what should it be? Well, we just talked about it. Yes, it is low enough. In fact, it could be a little bit higher, right? We could make this a little bit higher now. So if we wanted to, we could plug in and work the other way around from this equation. If we solve for r using our 0.15 as a coefficient of friction, then we could solve for v, sorry. So this should turn into v squared equals mu rg, and then square root both sides, mu rg. So v equals, and so now with our new coefficient of friction of that, radius of this times gravity, we should have 12.1 meters per second. Now keep in mind this is meters per second, so then times by 3.6. And you can see that you could go all the way to 43.6 kilometers per hour. Now, here's the problem though. Once you start sliding, what happens? Well, now you have kinetic coefficient of friction, which means you have a bigger problem. So this is your static coefficient of friction, but the moment that you go 44 kilometers an hour, you're hooped. You start sliding and it doesn't work out. Right? So this is really, really on the edge. So not really much can change here, given that result. Is the speed limit reasonable for all months of the year? Well, not really, right? We can base it off of wet and dry pavement. We can probably base it off of this 0.53. So we can now work this backwards again. So probably not. And we can go like this. Where mu is going to be that times 3.6. But mu is going to be 5.3. And I'm timesing by 3.6 to get it directly into kilometers per hour right away. So 82. Now that would be really fast, let me tell you. I've taken that corner many times, and that would be very, very fast to take that corner. But hey, that's what it says. It says we could make it, right? Now, some of the things that are not being taken into account is that when you have bumps on the road, you might slip into kinetic coefficient of friction, right? So again, maybe not quite taking it fully into account, but yeah, maybe the dry speed limit should be 80 kilometers an hour, because you can go faster. Okay, now, police radar is not accurate while cars are turning. This is true. In order to determine if a car is obeying the speed limits, police could use the period of a turn. How fast is a car moving if it takes 10 seconds to go around the semicircle in the image to the right? Okay, so this is now going to use we want to find the velocity, right? Now our formula is 2 pi r over t. But the problem is it's a semicircle, so it's half of a circle, right? So it's not going to be, now, so to be very clear, it's a semicircle, right? Which means that you're not going to use a full circle. Now, normally this is 2 pi r, because 2 pi r is one full rotation, which means like one period, right? But instead, we're going to just do half of a circle. So it's just going to be v equals pi r over t. Now, if we know that r, the radius, is 100, and it takes 10 seconds to go around the corner, that means they're going 10 times pi, so they're going 31.4 meters per second. Oh my gosh, they're gonna crash. Okay, 31 meters per second, because if that is correct, then we're gonna go 31.4 times 3.6, and they're going 113. Okay, maybe this example wasn't the best example, but there it is, kilometers per hour. So 113 kilometers per hour for this wacko driving around the corner. You can imagine that very quickly, if we move that value to be bigger, it would change our results. So we had it as 100 times pi over 10, but let's say it was 15. Now it's at 20, right? You try it again at 20. Now it's more reasonable again. So you can kind of see how, you know, they could figure it out, you know. They could figure out how fast you're going if they knew their physics. Maybe they don't. Okay, so yeah, this is circular motion. We're just talking in a horizontal sense. We will look at vertical circular motion more in the next video. Hope this video helped you better understand circular motion, and good luck.